A few weeks ago, I showed you here in a video how you can produce surprisingly large amounts of biogas from kitchen scraps and green waste with simple methods. Many people then asked me in the comments how the biogas generated could be used most effectively. Of course, the methane can simply be used for cooking, heating, or the direct combustion can be used in many different ways. The precious biogas can be used much more efficiently, and I have been trying to optimize this for a long time with my self-built Stirling combined heat and power plants. It is easy and almost free to produce impressively large amounts of biogas yourself using simple means. My small test plant produces around 200 liters of purified biogas per day with a very high methane content even in the cold winter here with little effort. A larger plant, 10 to 20 times the size, is already in the planning stage, enabling us to become independent of energy suppliers for electricity and heat in combination with our solar plant. Depending on the type of further use, it is very important to purify the biogas as much as possible. In particular, hydrogen sulfide can be harmful to health and corrosive. As shown in the video, I filter the biogas through rusted steel wool, which is perfectly sufficient for my needs. There are simple, even more effective methods that I have no practical experience with. But if you do a little research, you will find lots of information about them. Millions of small, self-built plants, mainly in Asia, produce biogas mostly for cooking. You can also, of course, run your gas heating system with methane or use the combustion heat for other uses. A combined heat and power plant offers a very efficient option in which an engine produces electricity and the waste heat can be used for heating and hot water production. On a small scale, this is one of the most effective ways to generate electricity as it allows the energy contained in the fuel gas to be utilized optimally. Perhaps the simplest method is to run a conventional combustion engine on biogas and use the waste heat from the cooling water and exhaust through heat exchangers. It is also possible to operate a gas turbine, steam turbine or steam engine, or a more effective organic Rankine circle. I have been developing combined heat and power plants based on the Stirling engine principle for a long time. In my opinion, this offers a number of advantages, but also presents some unsolved difficulties. External combustion is insensitive to impurities in the fuel gas. By preheating the combustion air, it is also possible to further increase efficiency using simple means. The Stirling engine is based on a very simple and durable concept that is well suited for continuous operation because of its quiet and low vibration running. This eliminates the need for a start-up and control system and allows the biogas to be consumed at exactly the rate at which it is produced. My Stirling engines with mechanical drive are powerful and reliable, but too complex, maintenance-intensive and therefore too expensive for economical energy generation. The high production costs of the Stirling engine are also the main problem with all commercial solutions. In the case of heat pumps for low temperature applications, for example, the Stirling concept has become very successful because the high costs for the Stirling are not so significant here. In order to generate electricity and heat in continuous operation, a maintenance interval of several thousand hours is necessary. However, the many moving parts in my mechanical Stirling engines require the wear parts to be reworked after just a few hundred hours. Therefore, I am now working with the thermoacoustic Stirling engine, the concept of which is incredibly simple and elegant. The fact that moving parts are only needed for energy conversion makes it possible to develop a very durable, low-maintenance and reliable motor using simple means. Furthermore, it is inexpensive and can be built by anyone without the need for expensive machinery. Only the power core, consisting of the heater, regenerator and thermal buffer tube, needs to be made from heat-resistant material, which can be ordered from a 3D printing company, for example, and is quite inexpensive nowadays. This means that an engine, which would otherwise cost several $1,000s, can be turned into a combined heat and power plant that is affordable for many. depending on how much work you put in yourself with 3D printed plastic parts, for perhaps as little as $100 to $200. I'm currently working on further developing the thermoacoustic engine and making it more powerful. The next major development step is pressure charging, which will be available soon and promises a dramatically increase in performance. Right now, I'm experimenting with various generator concepts for converting the thermoacoustic energy into usable electrical energy. These generators must, of course, offer good efficiency. They must also be durable and provide the possibilities to start the engine when it is closed under pressure. My experiments with a bidirectional impulse turbine, oscillating stepper motors, a conventional crank mechanism, and a very simple linear generator were all underpowered. I'm currently developing a more powerful linear generator. To achieve this, I'm using the finite element method, as well as stronger magnets, coils, and iron cores. I will then run intensive performance and efficiency tests on the generator. I hope that this will finally enable me to satisfactorily master the conversion of acoustic energy into electrical energy, which is crucial for the thermoacoustic engine. If I then manage to use a linear generator as a starter motor using a rather complicated coil control system, the first hurdles to a powerful engine will have been overcome. For this, I need a lot of development time and motivation. You can support me by leaving a comment on YouTube and Discord, becoming a channel member, or supporting me on Patreon. The more help and, above all, motivation I get from you, the faster the project can progress. All results and construction plans will be published in full, so that anyone can build their own combined heat and power plant, or just the engine, using simple means and little money once the first powerful prototype is ready. I would like to thank all my supporters on Patreon, all channel members, all viewers, and especially all comment writers for the help. I look forward to your criticism, suggestions and ideas in the comments here on YouTube and on Discord. Without your help, neither the engines nor the videos will improve. Thank you very much for your interest.